Okay, today's lesson is P1, and it is from a different packet, not in our book. I really like the way they teach the probability in these things. It was a class that I went to years ago. The title of this first packet is Probability Rules. We're going to start off with two basic rules here, the general multiplication rule and the general addition rule. What I want to tell you all about probability, there's a lot of reading, okay, a lot of word problems in here, but one of the main things is you've got formulas, and these two main formulas, especially in this particular lesson, if this tells you that one thing equals two things multiplied together, if I give you two pieces of information, you can always find the third. So just keep that in mind as we're going through and doing these. All right, so let's start off with the general multiplication rule. The probability that two events, A and B, occur at the same time is called the intersection of those two events. Okay, and the intersection can be determined by multiplying the probability of the two events together, with one of them being a conditional probability. So that's what you got to understand about this word, this notation here. Okay, so you have this is red, the probability of A and B. So that little letter there, it looks like an A if you put a crossbar in it. That's your and symbol, is equal to the probability of A times the probability of B given A. So that vertical line there is red given, and it basically says what's the probability of B happening, knowing that I know that A has already happened. Okay, so look at this example here. Suppose 35% of the farmers in a farming community grow carrots, and 70% of the farmers in the area grow peas. If the probability that a farmer grows carrots, given that he grows peas, is 40%, what is the probability that a randomly selected farmer grows carrots and peas? It's not a tongue twister, but I like to make it that. So I'm going to find out what they said carrots and peas. It's written peas and carrots. It will not matter. It is done according to the information that is given to you, but you'll get the same thing. So the probability of peas and carrots is the probability of peas times the probability of carrots given that peas has happened. So in our problem, what is the probability of peas? Well, it's 70%, which is 0.7. And the probability of carrots, given that he grows peas, right here is 40%, or 0.4. So I multiply those together and I get 0.28. If you want to write that as a percent, it is 28%. When you do your quizzes in Canvas, y'all, be on the safe side. Just always give me a decimal, and I tell you to give it to me to 3 places. So just pay attention to the directions. There might be 1 or 2 later on that you do more than that. Okay, so that's your multiplication rule, which is for and. Then you have your addition rule, and the addition rule is for two events where there's an or statement. And an or, the probability of event A or B occurring, is called the union of the two events. And you get the union by determining by adding the probability of A and the probability of B, and then subtracting the intersection of the two events, which is what you often get from something like this. So if we go back to that same problem, okay, what's the probability of a farmer growing carrots or peas? Okay, this is our symbol. This is our symbol for or. Okay, so the probability of carrots or peas is the probability of carrots plus the probability of peas minus the probability of carrots and peas. And as I just said, y'all, carrots and peas, probability of carrots and peas is the same as the probability of peas and carrots. So that number is what we're going to use for right here. So the probability of carrots is 0.35. The probability of peas is 0.7, and the probability of both is 0.28. So when you simplify that, you get 0.77. Okay? One thing that I want to point out, I draw because sometimes this helps people understand. But if you remember Venn diagrams, okay, and we know that the probability of both of them is 0.28, okay, and we know the whole probability of carrots is 35%, then what's left over here is 0.07. And if the probability of peas is 0.7, then you take that part out, and what's left is 0.42. And if you were to add up all three of those numbers, then you're going to get the 0.77. So it's just a little visual about the example we were just doing. Okay. Remember, and I should have started off with this. Apologize. I realized it wasn't in there. But the probability of any event happening, y'all, is always between two numbers, 0 and 1, because 0 means it's absolutely not going to happen. And 1 is, of course, absolutely it is going to happen. Okay. And as I mentioned before, you may give me an exact answer when you do your homework problems, or round it to 3 decimal places. That one, of course, came out to be 2. So it is technically rounded to 3 decimal places. Okay. So another type of problem that goes along with this is something called frequency tables. And I happen to love frequency tables because I think that they're probably the easiest of all the probability problems to do. So look at this one. Juniors and seniors at Memorial High School who drive to school have 2 options for parking. There's a reserved lot on campus that charges $10 per month to park, or students can park across the street in an open lot for free. The table shows the distribution of students' preferences by parking by class. So these are the juniors, these are the seniors, those who pay for the reserved lot, and those who don't pay for the open lot. And then sometimes you're given this total number and sometimes you're not. I'm sure y'all know how to find it if you're not given it. Okay. Now, I'm going to write the notation because I feel like if you can get that notation, some of y'all do it, don't write it down. But if you write down the notation and you always use the formulas, you'll pretty much always get these right. Okay. Sometimes it goes against the way people think, including me. Anyway, all right. So if a student is randomly selected from students who drive to school, what is the probability that the student is a junior? So I am straight up looking for what we call probability of a junior. Okay. Now, there are no special things to it. Probability of junior, which means my bottom number is the total number of students I have. So from my diagram, that total number is 650. How many of those people are juniors? Okay. And what I did up here, y'all, is I actually came and put a little dot next to it so you could see where I got that number. Okay. How many are juniors? 250. So 250 is going to go on top. And you always simplify that answer. And if you want to give me 3 decimal places, there it is. Okay. Now, what is the probability that the student parks in the reserved lot and is a junior? So I put a box around and because that's the key word. And that keyword and, remember, implies the intersection. Okay. Now, I'm going to write that in notation. So this is how I'm writing reserved lot and a junior. Okay. My denominator doesn't change. It's the total number of people. So I get that from right there. I didn't do that one yet. But anyway, 650. And then how many of them are reserved and a junior? So you can look at reserved lot and a junior. Where's the intersection of reserved and junior? Well, I have it highlighted in green. It is 75. So we're going to put that in and reduce it. And again, there's your decimal if you want the 3 places to your decimal. Okay. Now, this next one, what's the probability the student is a senior given that the student parks in the open lot? Okay. Whenever you have a given, your denominator is going to change. So that's the only time it ever changes. So I'm going to write my notation, probability of a senior and given, probability of a senior given open lot. And so when that changes, what's the given? Whatever comes after your given is your new denominator. So given the student parks in the open lot, how many students park in the open lot? Okay. Well, that's 450. I didn't want to do that. Go away. Anyway. Okay. So it's 450. And so 450 is going to be on the bottom. And then when you have a given, y'all, you're only looking in that column or row that you use the total. So out of those 450, how many of them are seniors? Well, how many are seniors? It is 275. So 275 is going to go on top when you reduce it, and there's your decimal rounded to 3 places. Okay. I think in the past I didn't do it, but I went ahead and did it on this video here. What's the probability that the student is a senior and parks in the open lot. So this right here is my key word, and, okay, writing my notation. Okay, so notice the difference between what we just did. That's the probability of a senior given open lot. This is the probability of a senior and an open lot. Okay, and uses the total of all the information. So that's why there's an orange dot up there next to 650. And how many of them are seniors and park in the open lot. So I'm going to look for the point of intersection of senior and open lot. So that is 275. So that's going to be on top. Reduce it 3 decimal places. Okay. The last one is an or. And remember from what we just talked about, the or statement is the union. And that is when I add. Okay. So when I add, again, I'm going to put my notation, which is my U. So that's the probability of a senior or open lot. Okay. I don't have the word given. So my denominator is still 650. Okay. Now I'm going to add anybody that is senior or parks in the open lot. So that is all of these that are highlighted in orange. Okay. So I actually put them down like this. Okay, put my little dots on that side because it was getting a little confusing. So this is what all of these numbers are. 125 plus 175 plus 275. Now, that's how you can do it from a chart, y'all. Okay, if you wanted to follow the rule that we had on the first page, then you would use the total numbers, in which case the probability of the total seniors, and then the total seniors would be 400, total open lot would be 450, and then you would subtract the overlap, which would be 275. So that's what that represents. So you can do it either way. You're going to get the same answer. Okay. Add those up or combine the top over your bottom and then reduce it, and there's your 3-place decimal. Okay. So that's the gist of it. Okay. What I want to do, I'm just going to get you set up on this next problem. Because sometimes when they give you a lot of information, it just helps to keep it straight. And if you'll put this information down first, it will make the rest of the problem solving easier. So it would help for you to get in this habit. So in this problem, in March, 2 types of salmon run in a large river in the Pacific Northwest. Researchers record the salmon as they pass through fish ladders on the river. So the information they give me, 42% of the salmon are Chinook salmon and the rest are sockeye salmon. So that statement is going to tell me what percent is Chinook, 42%. Well, that means you can tell me what percent are sockeye, because they both have to add up to a total of 100%. Okay. Of the sockeye salmon is kind of like saying, given that it's a sockeye, 35% are male. So the probability of male given sockeye is 0.35, which means you can go figure out what percent are female. And 45% of the Chinook salmon are male. So it's going to be probability of male given Chinook. And that, of course, is 0.45. And you can go figure out what percent are female. So one of the reasons I wanted to show you that is that these two are given statements that are written like that. So sometimes if you're not aware, that makes it a little bit more challenging. So hopefully that setup will make it very easy for you to finish those problems. And if you have any questions, I would encourage you to work with another partner with it when you do this packet. All of these probability ones until we get back to the book problems. It's a great thing to talk to people, and it just helps you understand it better. So hope that was easy. And please do not hesitate to email me or set up a Google Meet if you have any questions. Thank you so much, and you'll have a great day.